Hello again. Tonight we're going to talk about the CMB, the cosmic microwave background, and what is the longest wavelength, lowest frequency of it. So the CMB, this is a very low energy, low temperature collection of microwave photons that were left over from the Big Bang, the early days of the universe. It's everywhere in all directions, and we kind of sit within the shell of it. We're not likely at the center of it. These are very low energy photons near 0 Kelvin. I think it's around 3 to 5 Kelvin, well below human visible light. So we have to see it in things like radio. It's down in the microwave region, so we don't even see it in infrared. Collectively, since it's everywhere, the CMB actually has more energy than the current universe because it's kind of left over from the Big Bang, which was a Big Bang, and therefore all this energy is still collectively greater than all the stars. So what is bandwidth? So if you have a photon, a particle of, I don't want to say light, just electromagnetic energy, it has energy, it has a wavelength, a frequency, and when you have a bunch of them, that's called a flux, not a flux capacitor, that's something different. But you have a flux of photons, and it has a range of frequencies, wavelengths, that's its bandwidth. It has a center point that's between its minimum and maximum range, and it has a peak. That's the bunch of photons with the highest energy level, the highest amplitude within that range, which is not necessarily the midpoint, may be offset. The range or the bandwidth is defined as frequencies or wavelengths, and frequencies are from the low frequency to the high frequency, and they're scaled in a unit called hertz. And that was formerly known as cycles per second, or how many wave cycles from peak to peak or valley to valley per second. And it can be billions, so gigahertz, or millions, megahertz, thousands, kilohertz, or just hertz, or even fractional hertz, which is controversial as to whether fractional hertz exist or not. The wavelength range, it's a length, it's a distance, min to max, it's scaled typically in meters, not feet or inches. And it starts out very small as billionths of a meter, or nanometers, and it goes to millionths of a meter, or micrometers, thousandths of a meter, millimeters, and then meters. And they get really long, they go to thousands of meters, kilometers. And then when they get really long, they just go to light year distance, which is 5.9 trillion miles, multiple light years. And they have measured gravity waves in light years wavelength, but they haven't measured photons in light years wavelength. And we'll get to why it's hard to measure fractional hertz. The contemporary observations that we have made of the CMB frequency range is supposed to be from 300 megahertz to around 630,000 megahertz, or 0.3 gigahertz to 630 gigahertz. The peak, where the amplitude is the highest, is about 160 gigahertz, and the bandwidth from low to high is 629 gigahertz. Convert that over to wavelength instead of frequency, and you get 0.3 millimeters to 1.9 millimeters. That seems quite narrow, but if you realize that they've been looking at it in microwaves, this kind of explains it, because that's microwave range emissions. Depending upon who you're talking to, they might want the number expressed in frequency or wavelength. If you're talking to ham radio folks, they like to talk in scaled meters of things, like 4-meter band or the 12-meter band, whereas scientists will often talk about things in wavelengths if they're really small, because they'll talk about nanometers, like the wavelengths of light. They measure in typically nanometers until they get down into infrared, where it's longer. And they talk about millimeter wave and microwave radio and things like that. So who you talk to, they'll mix and match frequency and wavelengths. So is the actual bandwidth, the max and the min of the CMB, really just a matter of, well, based upon the instruments that we use to observe it, that's the minimum and maximum for those particular instruments? Or is there really nothing higher and nothing lower? Well, it turns out that there are actually higher and lower, but because that's the instruments we've sent up there, that's the presumptive lower limit of the CMB. And why are we describing the lower limit based upon the instruments as opposed to the actual lower limit? So on the left, you have the electromagnetic spectrum. At the top, you have the very shortest ones. Those are gamma rays. And then it goes down through visible light, microwaves, down to short waves, medium waves, long waves, radio stuff. So it goes from particles into wavelengths of visible, and then down to radio, and then longer than radio. If you were to take that 300 megahertz bottom end that they say CMB has, look on the left, that little inset where the red 300 megahertz text is, UHF radio is above it. And if you look from the outset, the bigger one, microwaves are above it. Radar in microwaves is above it. So what they're saying is the low end of the CMB is actually lower than microwaves. It's into near very high frequency radio wave, down near where the old TV channels used to be. But if that's the case, why, if you're in high school and they talk to you about the CMB and kind of physics, astronomy, they'll tell you, and you used to be able to see the cosmic microwave background on your analog TV. If you tune to like channel 3 between two allocated channels, you get that white random sparkly stuff. They're here, and you get the hiss noise. That was partially attributed to the CMB. It's everywhere. It's omnipresent. You just have to tune where there's no TV station on an analog TV, and you could see the CMB. And if you had a radio, you could take your FM radio and tune between stations, and you would hear static. You'd hear hiss. And that was the general background of the CMB. And that's what they used to tell you, is that's due to the CMB. Not all of it, but a percentage of it is due to the CMB. Well, if that's the case, and you were watching it on an analog VHF TV or listening to it on FM radio, that's well below 300 megahertz. FM radio, that's down around 88 megahertz, not 300, down to 80. What gives here? Well, actually, it's what we know the bottom of the CMB to be is the instrument's bottom, not the actual, can we see anything lower? If you get down that low and you start saying, well, I can hear it. We used to listen to it on channel 3, which is down towards the bottom, down towards 50 megahertz, more like about 70 or 80 megahertz. So that would be n times meter wavelengths. That's very long wave. So how do we see more CMB stuff? Because remember, we looked at the CMB and microwave because that gives us the farthest back look towards the Big Bang at about 500 million years after the Big Bang. Well, what if we were looking at other things like neutrinos or X-rays or gravity waves? And this has been postulated because we have instruments that can observe at these levels. Neutrinos and gravity waves are intermittent. They're not always there. Like if at night you go out and you look at Rigel, a star in the Orion constellation, if you can see Orion, if there's no clouds in the way, it's not below the horizon, Rigel's always there, it's always bright, you can always see it. If you're looking for neutrinos or gravity waves, they're not always there. You have to wait for them to show up, and they're very short in duration. So if you're attempting to scan the sky in neutrinos or gravity waves, you're going to have gaps where, I'm sorry, an event hasn't taken place in that part of the sky, so we have nothing to observe. X-rays. A few weeks ago, I mentioned that NASA wants to stop funding Chandra, which is our Earth-orbiting X-ray telescope. That would mean the U.S. can't see an X-rays in space. The European Space Agency wants to stop funding their XMM Newton X-ray telescope in 2026. They don't have a plan to replace it until maybe 2028 at the latest, if they're successful, if they get the budget money that they want. So if Chandra is turned down and then Newton is turned down, you'll have a gap where we don't have any good X-ray telescopes left. They're all turned off. So no replacement for Chandra. ESA doesn't have a confirmed replacement until maybe 2028. Can't observe an X-ray. Even if you could observe an X-ray, X-ray telescopes have a narrow field of view, and there'll be gaps where you're not pointing at a place where there's X-rays. You might see stars, you might see quasars, but you won't see open space because there's no energy there. So I said, well, I can think of an alternative. Why don't we define, since we're already looking in radio and microwaves, why don't we continue that progression down to longer wavelengths, lower frequency? Design a radio space telescope capable of looking at a narrow field of view and a broad range of low frequency, long wavelength signals. And these would be a variant of something called the Yagi-Uda antenna. This is sort of that wedge where you see a rod and it's got little 90-degree bars on it, and the bars are short at the front and longer at the back. Those are very good for a wide range of frequencies, narrow field of view, high amplification. Have a couple of those on your space telescope and cover multiple frequency ranges. Put it in space at L2, so it's out beyond the moon, in orbit around about the sun with the Earth, just like JWST is, just like Gaia was. But put it into a L2 virtual orbit smaller than the lunar diameter. The reason for that is the moon will block out the radio frequency interference from the sun and the Earth. The Earth has a lot of RFI, radio noise. We can block out that because it would be hiding behind or in the shadow of the moon. To communicate back with Earth, you would use a orbiting radio relay satellite like the Lunar Reconnaissance Orbiter, which has relayed things up from the lunar surface back to Earth. You could point your antenna on this radio telescope back to the LRO and relay to Earth. This radio satellite could use inertial navigation to point up, down, and left, right. But then as it moved around its L2 orbit, it could see different parts of the sky and capture the CMB at very much lower frequencies than even microwave. If it can see down into kilohertz range, then you would be looking back another maybe 100 million years closer to the Big Bang. That would be the earliest that we could, by our current technology, see to the Big Bang. We can observe farther back than in microwave. You can't do this from Earth atmosphere because that particular wavelength gets blocked by the ionosphere and you won't be able to see space. You can't put it in Earth orbit because the Earth has a lot of radio frequency interference. And if you put it in Earth orbit, the sun would go by. So you need it in shadow. Well, if it's out at L2, it's always going to be pointing away from the sun, just like JWST is. And you can't ever point it towards the direction of Jupiter or Saturn. Even if that's the part of the sky you want to judge, you have to wait until the Earth orbit around the sun takes you further around. And now you can put it there if Jupiter and Saturn are off the site, because Jupiter and Saturn are natural radio sources. So they would be their own natural radio frequency interference. But hey, look, somebody's already kind of done this. Not the US, not the European Union, not Canada. It was the Netherlands technology in conjunction with the Chinese Space Agency, the CSA, but not to be confused with the Canadian Space Agency. They did a ride share. China wanted to deliver a payload out to L2. And so they said, do you mind if us poor Netherlands folks put some of our technology aboard your L2 satellite so that we can observe in radio? And they did. It was called the Netherlands Chinese Low Frequency Explorer, or the INCL, but not man from. It had, if you look in the upper right, there's a diagram of it there. Those three sticks you see sticking out are monopole antennas. So they individually see in all directions, and they're lying flat from the perspective of the satellite. So as the satellite in orbit with the Earth around the sun sweeps the sky, they can actually scan. And by having three antennas, the phase of the photons can be judged. So it can kind of get a narrower field of view and know which direction it's pointing, but it's still very coarse. It has an angular resolution of 1.5 radians. And for those that aren't into such things, that's 86 degree field of view, which that's fairly broad. That's way wider than the diameter of the moon. The moon's a half a degree. The good part was it had a very wide reception bandwidth from 80 kilohertz, which is kind of down into the AM band, up to 80 megahertz, which is kind of the low portion of the FM radio band. But you can see that the wavelengths are down to low end 3.747 thousand kilometers, very long wavelength, up to 3.7 meters. So a very broad range. This was launched aboard the Kekiao Qiang-4 lunar relay satellite. It was launched into a figure-8 orbit about L2. It had a long Lagrange's orbit because that way it could see back past the moon and communicate with Earth. You've never heard of this particular Netherlands Chinese satellite program or radio astronomy from space? I look at a lot of different news content. I did not have to look at any Chinese news content to find out about this. But once I found out about it from a Netherlands news content, then I had to go back and look up the details of the multinational agreement that allowed them to do this. They were given payload weight of 10 kilograms and a power budget of 50 watts on board this satellite. Just to let you know that the low frequency, the 80 kilohertz, for about $25 to $30, a hobbyist can buy a quantity one off the shelf from Amazon software-defined radio that not only gets you down to 80 kilohertz with the right antenna, it can get you down to a single-digit hertz. And one of the largest radio frequency interferences from the Earth is the power grid. You don't think of the power grid as a radio source, but it's at 60 hertz in the US, and it's at 50 hertz in the UK. That's a very high power, very high amplitude radio interference source. So you need to, if you're going to be receiving from the Earth as your place where you're listening from, you need to notch out the power grid. And the power grid, because it's kind of not precise, it sways a bit, there are harmonics. So not just 60 hertz, but 120 hertz, and it gets lower amplitude, but you've got to put a couple of notches there. Is it technologically feasible to listen to these very low frequencies? Absolutely. So is this a progression with no end in sight? As we look into redder and redder parts of the electromagnetic spectrum, we go from gamma to X to UV to visible to red to low infrared to medium infrared to deep infrared, and then we get into radio, microwave, shortwave, long wave. The further we look deeper, we still find stuff there. Longer wavelengths, we go from nanometers to meters to kilometers to Earth diameters to light year. We decrease the frequencies. We go gigahertz, megahertz, kilohertz, hertz into fractions of a hertz. The individual photons have an energy level that high energy, like X-rays and such, you're going to be in the gigahertz range. But then as you get down to ultraviolet, into visible, into infrared, you start getting down into the kilo electron volts and then electron volts. And just as you can get into fractional frequencies, you should be able to get into fractional electron volts. So if we continue this, how low can we go, so to speak? Well, it turns out that in order for the particular effect to work that allows us to take a photon and convert that into a power level, an electron that we can measure with an analog to digital converter, we need elements that when this photon interacts with them, it makes it spit off an electron. It ionizes an electron off. But as we get to lower and lower energy levels, it gets more and more difficult to find materials from the periodic table of elements that can become excited. And as it turns out, the lowest elemental excitation level in the periodic table of elements is cesium at 3.8939 specific value electron volts. So if we know that this progression is going to take us down to fractions of an electron volt, how do we detect them? We're going to have to come up with some new technology other than the photoelectric effect that will allow us to take these photons in and produce electrons out that we can then measure as a signal, as an observation. If these photons can get lower and lower and lower in energy, and it's open-ended back to the earliest part of the universe, how many of these photons, what is the flux of these progressively weakly or non-interacting photons? Is there a limit to them? And once they drop below the interaction level, do they still interact with anything? If they're not measurable, are they still there? Infrared had to be discovered. It's been there all along, but until somebody put a thermometer at the bottom of a spectrum, they didn't realize there's heat down there that we can't see. Well, it could be that there's a whole range of photon frequencies and wavelengths well below 1 hertz that are many, many, many meters long, maybe Earth diameter long, that we don't have any technology for detecting, but might still be there. And as we found out from the 2018 Nobel Prize for Photonic Tweezers, if you have photons, they have not mass, but they have energy, and the energy can be conveyed as momentum. So if you have a photon interact with something, it transfers that momentum to what it interacts with. And based upon the reflection angle, you can get a percentage of that momentum transferred into the object. That's on a per photon basis. But if you have a high enough flux, a 5 milliwatt infrared laser, and you shine it onto a bacteria, a single cell of bacteria, the bacteria will move across your X-ray microscope. So that's what the 2018 Nobel is about, is you can take an infrared laser, which is a concentrated flux of photons, and use those photons through radiation pressure to move things. That's one cell. If you have a high enough flux of these, maybe you can move things at a very large scale and not detect them because they're so weakly interacting. This may be the photons you're looking for dark energy or dark matter. Just, connecting the dots, thinking outside the box. So in summary, if you think about your own personal observations of the CMB, watching it on an analog TV as snow, maybe the bottom end is much lower than COBE or WMAP or Planck profess it to be, because that's just the bottom end of their instruments. We're already far longer into microwaves. We're down below the bottom of microwaves. Even with the Planck observations, there's no bottom there. It keeps going down. We just don't have the instruments for it. Do what the Netherlands did, develop a space probe that has specific instruments for getting down into being sensitive to the lower and lower frequencies, longer and longer wavelengths, and put it at L2 so it has a good chance of not being drowned out by Earth RF noise. Talk back to Earth indirectly through a lunar orbiter, and allow it to do scans of the cosmic microwave background well below microwave. Don't go with trying to observe in X-rays or gravity waves or neutrinos, because you're just not going to be able to do a comprehensive scan like you've done in microwaves for the CMB. And what's the bottom end of this wavelength energy progression? Do photons become non-detectable, dark, or do they still exist? And then we have lots of links. And then I do have the Russian-based radio telescope, and then the Netherlands, China one. As of 2023, the NCLE hasn't produced a conclusive paper on their observations. Comments? Question?
What do we expect to see at such low frequencies?
The CMB image we have from Planck is obviously not in visible colors, but they artificially mapped the particular energy levels for each wavelength onto colors, and that's how you get the blues and the reds and the oranges. It'll be the same thing. It will be receiving energy levels, much lower, but energy levels that vary, and you'll have a similar sort of map. You'll be looking to energy that is farther and farther back. It won't be at 500 million years after the Big Bang. It might be 1 or 200 million years after the Big Bang. You're seeing farther back. And if the WMAP sort of observations of CMB taught us things about the earliest billions of years of the universe, we might learn similar things to extrapolate back even further. We might find that, because the CMB collectively is more energy than we have in the universe today, it may be that we see even more energy. So while the wavelength will be longer and the frequency will be lower, the amplitude could be much higher. It'll be interesting to see what we see when we actually try and see it. But we can't see it from the Earth's surface. We can't see it in Earth orbit. We've got to get out there, and we've got to have the right kind of instruments and antennas to get out there.
Yeah. It seems to me that technology is always pushing.
Yes, good.
That's fine, yeah. But I wonder what they might expect, and they're just going to see more of the same.
Well, there are people in the radio realm and some of them in particle physics that will say there really is no such thing as super low frequency radio. In other words, radio where the frequency is a fraction of 1 hertz. It takes more than 1 second to get a single wave to propagate. And I'm like, why? Why would it stop at zero?
Yeah, but propagate it does.
It should be more than capable of being fractional. Negative is the question. Does it go below zero to negative?
Yeah.
Don't know. That one I think would be an interesting question. But at the moment, we're still stuck on below about 8 hertz is where you start getting into the super low frequency stuff. And the wavelength is more than Earth diameter long. So they'll say things like, you'd have to build an antenna that's bigger than the Earth. Do you remember when cell phones first came out and they had that whip antenna on them and you had to extend the antenna? Well, they moved to different frequencies and the antenna got shorter.
Yeah.
But the antenna in your mobile phone now is what is known as a fractal antenna. It is a fraction of the wavelength that you're actually communicating on. So it is possible using a digital signal processor for you to have an antenna that is quite a bit smaller than the wavelength of the radio waves that you're listening to.
Yeah.
You just need the antenna to be shaped to pick up and trap the photons.
There are always improvements, breakthroughs.
And that's the thing is we just need people paying attention and expending the resources, the effort to make these breakthroughs instead of going, that's not possible. Luke, I am your father. That's not possible.
Yeah. The first time I heard about frequency synthesizers, I couldn't believe such a thing as that. You need a crystal to make a frequency, right? No, not anymore.
No. You just need electronic closed loop circuits. It's fascinating. I've studied the chips that make up software-defined radios. How do you tune the receiver to tell it what frequency you want to listen on? Well, they have an oscillator that produces a frequency, and then they use a circuit that does a closed loop back against that frequency and beats against it. And when it syncs up, you'll be receiving on the frequency that you've tuned. Okay, I can understand that. It's a bit weird, but yes. So now you have a tuner that has no moving parts on it, no dials, no knobs. It's just got a number. And the number is a digital to analog converter for this closed loop to drive the frequency back into itself to listen on that wavelength and exclude all others.
A whole new way of looking at things. Yeah.
It's, once you start applying digital technology to what you thought of as an analog natural signal, there's all sorts of things you can do to it. They used to have a lot of different radios inside of mobile phones, and nowadays they just have a very capable digital signal processor that has multiple cores on it, and each core is assigned a different frequency range. So instead of having a dedicated, separate little circuit board component for your Bluetooth, your Wi-Fi, your different frequency Wi-Fi, your RFID, your 4G, your 5G. Now you just have one complex digital signal processor that has multiple cores, and you just run an algorithm for each band you want to be communicating on. Any other comments or questions before I stop recording? Hearing nothing.